Okay, this is video 28.1. We'll be looking at Kirchhoff's loop rule. Again, this is mostly review from last year. The first thing we need to do is define EMF. EMF means electromotive force, which is a term I don't particularly like because it's not a force. It's essentially the same thing as voltage, but applied specifically to batteries. So if you have a battery with EMF curly E, that means that as charge passes through the battery, the amount of energy that the battery gives to that charge is charge times the EMF. So it's just the same thing as battery voltage. And ideal batteries, which are generally what we'll assume we have, just have an EMF. Every time a charge goes through the battery, it picks up this much energy. However, real batteries have internal resistance. And so a real battery is going to be an ideal battery with EMF curly E in series with an internal resistance R. And all of that is inside the battery. So you've got an EMF and you have an internal resistance. And the result is if you measure the terminal voltage across the battery, that will be reduced by the internal resistance. And the more current flows through the battery, the more the terminal voltage is reduced. The equation ends up being that the terminal voltage equals the EMF minus the current times the internal resistance. So when the current's zero, the terminal voltage is the EMF. But if you start trying to pull a lot of current from the battery, the voltage drops, and sometimes that can screw up whatever's being powered by the battery, which is a pretty good description of how real batteries work. Internal resistance for batteries is typically very low, just a few ohms for alkaline batteries, milliohm range for things like car batteries. Now, what Kirchhoff's loop rule says is that if you have a loop in a circuit, you add up all the voltages around it, and you'll get zero. So, very simple circuit. Let's say that we have a battery and a resistor. What this basically said is if we go around the circuit like this, the battery voltage minus the resistor voltage equals zero. And it's a statement of conservation of energy, because if you imagine an electron taking this path, it picks up energy in the battery, it goes through the resistor where it loses some of that energy, it turns into heat, and then when it gets back to the same place, it has the same zero energy that it did before. And if it didn't, as this electron goes around the circuit again and again and again, it will gradually be picking up energy, and that's just a non-physical result. And so you need to know that Kirchhoff's loop rule is a statement of conservation of energy. Now, when you apply it, you need to pick a direction to go around the loop, and you have to go all the way around the loop. You can't stop in the middle. And you need to guess the direction of the current through each resistor. It's okay if you're wrong. If you're wrong about the direction, you'll just get a negative number when you calculate the current, and that'll tell you, oh, I guess wrong. But in general, if you're going, like in this case, we're going from the negative terminal of the battery to the positive terminal of the battery. So for batteries, if you go from negative to positive, you're going to add the battery voltage. If, on the other hand, you go the other way across the battery from positive to negative, you subtract the battery voltage. For resistors, on the other hand, if when you get to them in the loop, you are going in the same direction as the current, then you'll subtract the resistor voltage. And if you're going in the opposite direction as the current, you'll add VR. The reason for this, like in this circuit, we would guess that the current goes that way. And so we're going in the same direction as the current, VR. The reason for that is that when you have a resistor, the current flows from the high voltage side of the resistor to the low voltage side. And so if you're going in the same direction as the current, you're going from high to low, and so you have to subtract that voltage drop. Now, it's very simple for a single loop circuit, more complicated for multi-loop, but for now we'll just look at the single loop. And so let's say that we've got 3 resistors in series and with a battery. So I'll say that the battery voltage is E, and then you've got 3 resistors, R1, R2, and R3. Now, the first thing for the loop rule, we have to guess the direction of the current through the resistors. And this is a pretty easy one. I'm going to guess that the current goes downward through all 3. Now, the other thing is that because they're in series, I can say that they all have the same current. Because once the current goes through resistor 1, it's got to go somewhere, and really the only place it can go is then through resistor R2 and resistor R3. Now I'll apply the loop rule, and I'll have my loop go in this direction. So if I start here, the first thing I do is I go across the battery, and I'm going negative to positive, so I'll add the EMF. And the next place I go is through R1, and I'm going in the same direction of the current, so I will subtract voltage V1. For the same reason, I'll subtract voltage V2 and voltage V3, set that all equal to 0. Now the other thing I can say is that the voltage V1 equals I times R1, V2 equals I times R2, and V3 equals I times R3. And so this equation turns into EMF equals I times R1 plus R2 plus R3. So the current becomes EMF divided by R1 plus R2 plus R3. And you should recognize from last year that that R1 plus R2 plus R3 is the equivalent resistance of the combination. And then if you're going to find the voltage across each resistor, let's say V1, that equals I times R1, so that equals the EMF times R1 divided by R1 plus R2 plus R3, and similarly for V2 and V3. You can plug in numbers if you want. So that's a very simple example how you use Kirchhoff's loop rule. Well, we're not done yet though. We want to calculate the power from the battery. Now the power from the battery equals the EMF times the current. And so if we plug in the expression for current we get the square of the EMF divided by R1 plus R2 plus R3. And if we want the power dissipated in each resistor, we can use I times V, where I is the current through the resistor and V is the voltage across that resistor. But a better thing to do is use the equivalent expression I squared R. And for the power through resistor 1, I squared is EMF squared divided by R1 plus R2 plus R3, all squared, times R1. And similarly for resistor 2 and resistor 3. And you'll find out, if you want to work this out, that the sum of the power outputs of the 3 resistors is equal to the power of the battery, which is a useful result, but not very surprising, because it tells us that all of the energy that the battery puts into the circuit comes out of the circuit in the form of heat from the resistors. Now, tomorrow I'm going to check questions 2 and 9 from chapter 28. Next video we'll look at multi-loop circuits, and then after that we'll look at capacitors and circuits.